right, let's get started. I again apologize for the delay in grading, but midterm 2 finally would be done by tonight. And the term break grade should be assigned by tomorrow morning. And then I have slots for one-on-one meetings if you guys want to meet starting Wednesday and for maybe a week after that. Homework 5 is unfortunately also delayed just because there were quiz and midterms, but that again should be done in a couple of days. Are there any questions on any of the grading or logistics? All right, so we were looking at the minimum spanning tree problem last time, where the problem is you're given a connected undirected graph G, and every edge has a cost. And what you want to figure out is a minimum spanning tree of that graph, which is defined as you pick a subset of edges that connect all the vertices. And under the assumption that all edge weights are strictly positive, if you want to minimize the total weight of the edges or cost of the edges that you pick, it has to be a tree. So we looked at 3 algorithms to compute the MST of such an input. They were all natural, they all work fine. One of the algorithms, reverse delete, we are not going to consider anymore. It's left, the proof of correctness is left as an exercise, but we are going to prove the correctness of Kruskal and Prim's. So just as a reminder, Kruskal's algorithm, it sorts the edges in increasing order of cost and considers each edge in that increasing order. And if adding that edge doesn't create a cycle among whatever it has already picked, it will put it in. If adding it in creates a cycle, it will not add it. Okay? And so this just kind of walks through all the M edges doing these checks. Prim's algorithm is very similar to Dijkstra's, and here you kind of build a set of nodes that you have already handled. And for this, you need a start vertex too. It doesn't really matter. You pick any vertex as S, and you'll be fine. And what you do at every step is, while you have considered the set of vertices in S, if there is an edge that's a crossing edge, so one endpoint is in S, the other endpoint is not in S, you look at all possible crossing edges and pick the one with the minimum cost, and you add the other endpoint into this. Okay? And you keep on doing this till there are no more crossing edges. And actually, it turns out since we have assumed that the original graph is G, G is connected, then the only time you won't have any crossing edges is when you have considered all the vertices. So you repeat this loop till S is not same as V. So as we talked about, there's an old history of these MST algorithms. They've been around for a while. In fact, there's a 4th one due to Borufka that we did not consider, but I think there should be time in the recitations for the TAs to go over it. Okay. So one of the things you might notice about this picture is that they're all old white dudes. Right, and so, I mean, there are many reasons for it, but the demographics of researchers in theoretical computer sciences is much more varied, thankfully. How many of you know who these 2 people are? I claim all of you should know who they are. Yeah, so this is John Kleinberg and Eva Taudos. They wrote your textbook, so that's why I said all of you should know who they are. This is how they look. In fact, there's actually their pictures in the textbook too. Okay. John also has a Buffalo connection. His father was a professor in the math department. He, while being a high school student, did some stuff in the department and so on and so forth. All right, so here are all pictures of people who do research in theoretical computer science. So this includes algorithms as well as complexity. Can you guess the common link between them? Yeah, Evan.
I was going to say they're all researchers.
Well, no, they're all researchers in theoretical computer science, so I've taken that off the table. Tyler.
They all got C's in undergrad algebra.
No, they did not all get C's in the undergrad algorithms. That actually is not the norm, but. Any other guesses? Steven?
That they all came up with different ways or some similar ways to solve the same problem.
Steven's question is, did they try to solve the same problem in different ways? No. Evan?
They all came from the same university?
Evan saying they all came from the same university. Nope. All right, so instead of playing this game for the next hour, let me just give the answer. If for whatever reason you wanted to go meet with them in person, you can. They're all within driving distance of 3.5 to 4 hours from here. So if you look at all the schools that you can get to within 3.5 to 4 hours, they're all here. Actually, Sophia and Adam have moved to BU, so they're no longer there. But over the summer, this was still true. So I just wanted to point out for two reasons. One, there is an incredible group of researchers in theoretical computer science fairly close by. And hopefully, as the picture shows, the demographics is much better, much more diverse. All right. Side note, this is not working. Bobby is brother of John, and both are professors at Cornell. All right, sorry, a couple of other things. Stephen Cook, he's at Toronto, he's one of the Turing Award winners. He basically was one of the co-founders of the P versus NP problem. Manuel Blum, who is at CMU, is one of the fathers of cryptography and a bunch of other stuff. All right, so let's go back to some technical stuff now. So the way we're going to prove the correctness of Kroes-Kelk prims is we have one algorithm, which I'm calling the cut property lemma. And here's what the lemma states. You have to assume that the all edge costs are distinct, so the lemma only holds under this assumption. So we're going to make this assumption to begin with, and later on we'll see how we can get rid of this assumption. And what this lemma says is, for any cut, a cut is just a way of dividing the set of vertices into two non-empty parts. Okay, so one part S, which is non-empty, and you have another part V minus set, which is the remaining part, which is also not empty. So all this is saying is S is not the empty set and S is not everything. So any non-trivial way of dividing the set of vertices into two parts, you look at all the crossing edges, let E be the cheapest crossing edge. And note that since the edge costs are distinct, there is a unique cheapest crossing edge. Then what this lemma says is, this cheapest crossing edge is going to be present in all possible minimum span trees of this one. This is a very strong statement. So the way we're going to use this is to argue that any edge that's added by Kruskal or prims will be the cheapest crossing edge in some cut in the graph. And so this lemma says, well, that has to be present in all MSTs, so the algorithm can't go wrong by picking it. Okay. So this is how we are going to use it. So we are going to prove the cut property lemma and then prove correctness of prims and Kruskals using cut property lemma. We're actually going to state the lemma first, use it to prove the correctness of prims, then prove the cut property lemma, and then argue the correctness of Kruskals. So that's how we are going to go today. Are there any questions? All right, so we're going to do the cut property lemma. So I said, assume all the edge costs are distinct. Then for all cuts, so again, cut is S and everything else, such that S is not the empty set and S is not everything. Okay, so both S and the other part are non-empty. So you have S and you have V minus S, and you look at all the crossing edges if E is the cheapest crossing edge, then that implies E is in all MSTs. All right, so I said we're going to, for now, assume this is true. So assume true for now. And we are going to first argue that Prim's algorithm is correct. So the first result we're going to argue is Prim's algorithm is correct. What this means is that the set of edges T that's output by the end at the end of run of the Prim's algorithm indeed forms a minimum spanning tree. And by the way, when I say assume the cut property lemma, we'll also assume till I say otherwise that all the edge costs are distinct. So we're going to go with this assumption for a bit and yeah.
Does that be a subset of V?
Yes, so Evan's question is, does S have to be subset of V? Yes. Yeah, so dividing, essentially what they're saying is dividing the set of vertices into two parts, both of which are non-empty. All right, so again, as I said, the idea is what we're going to argue is every point of time, Prim's algorithm adds an edge to T. We're going to argue that it is the cheapest crossing edge for some cut. Okay, and then what that means is Prims cannot go wrong by adding that edge. Okay, so consider the point when Prims is about to add an edge E to T. And I said our goal will be to argue E is the cheapest crossing edge for some cut S and V minus S. So to do this, what we have to figure out is what should be this cut. So again, I'm trying to add this edge E, and I want to figure out a cut for which this edge E would be the cheapest crossing edge. Now, if you look at the statement of Prim's algorithm, what is a good candidate for this set S? And I've chosen the letter S very carefully. Sorry? Matt? Right, so if you look at the statement of Prim's algorithm, there is already a set S, right? So that S is going to be the S that we want. And now if you remember what Prim's algorithm does is you have this set of S that are already connected to your original start vertex. You look at all crossing edges, and the edge E that you add to T is the cheapest crossing edge. In other words, the statement of the Prim's algorithm is literally using the cut property lemma to pick that edge E. Okay? All right. So, idea, apply the cut property lemma. So the S in the lemma is exactly the same as S in the algorithm. So again, as a quick reminder, here's how Prims work. You had this set S at some point, and you're looking at all possible crossing edges. And what Prims is doing is picking the cheapest crossing edge and adding it to T. So as I said, if you pick the cut defined on the set S that's used by Prim's algorithm, then by definition it's picking the cheapest crossing edge, and then this should be safe. Okay? So by definition, CE is the cheapest crossing edge. Now, we want to be precise, so just saying that by itself is not enough, because note that to apply the cut property lemma, you need to satisfy two properties on S. First, S has to be non-empty, and second, it should not be everything. Right? So we have to make sure that these two conditions hold. So claim 1 is S is non-empty, and this just follows from the fact that the first line in Prim's algorithm says add the start vertex to the set S. Right? So the moment you start running Prim's algorithm, your set of vertices S is non-empty. Okay? So as the start vertex is in this set S, which is good. Claim 2, S is not everything, because at this point the algorithm is trying to add the edge E. So let's say one endpoint is U, the other endpoint is W. Then since UW is a crossing edge, by definition W is not in S. Right, so again, crossing edges is one endpoint is in S, the other endpoint is not in S. So just by the fact that you have a crossing edge implies that there is a vertex that's not in S. And this is all you need to make sure that the cut is non-trivial, right? So both parts are not empty. So that implies adding E is safe as E is in all MSTs. Okay. So we basically argued anytime Prim's algorithm adds an edge, it is fine, because that edge is going to be present in all MSTs. Okay. All right, so what I want to do is talk difference for half a minute, let me know any questions, and I claim the proof is not done. So the proof is not done, it's not a complete proof. So if you don't have any questions, try to figure out what we still need to prove to complete the correctness of Prim's algorithm. All right, let's come back. Mehmet, you had a question? Right, so the question was, so what we have argued here is we're saying, look at the run of the Prim's algorithm. What we're arguing is any point of time you add an edge to this set T that Prim algorithm is building, that is present in all MSTs. That means your algorithm has to output that, right, because it's present in all MSTs. That's what we have argued so far. Any questions on that? Alex?
So we're adding E's that are guaranteed to be in all MSTs. Does that mean that there's only one MST?
So Alex's question was, we are adding all edges that are in all MSTs. Does it mean that there are only one unique MSTs? It doesn't immediately follow, but in this case it is true. So here is one fact, which is a good exercise for you to do at home. If all the edge costs are distinct, the MST is always unique. Okay, so in that sense, when I'm saying it's in all MSTs, it's in all MSTs because there's only one MST.
So by our assumption that all the weights or the costs are distinct, then
Yeah, so but that is not what we're going to use in the cut property lemma, and that is not how we're going to use the cut property lemma. But that's a separate theorem you can prove that if all the edge costs are distinct, then the MST is unique. You cannot have two distinct MSTs. It's actually not that hard to prove. It's a fun exercise to think about. Are there any other questions? All right, so I claim that the proof is not complete, so what's not done yet? So again, all I've argued is every edge that prims add is present in all MSTs. But why is that not enough? Matt?
You need to argue that it adds enough edges to make this thing.
Right, so the statement that I said that every edge that's added by the algorithm is present in all MSTs is also true for the terrible algorithm that doesn't add any edges. Right, if I didn't add any edge, then the statement that every edge that the algorithm adds is present in all MSTs is vacuously true. So the thing that has not been argued so far is that it adds all that it needs to. In other words, we have argued that everything that it adds is present in all MSTs, but we have not explicitly argued that the thing that comes out at the end is a spanning tree. Right, so we added, every edge that's added is a good edge, it should be added, but we have not argued that overall at the end it's enough. Okay, so that's the part that's missing. So we still need to argue that the final T is a spanning tree. And so we are not going to do it in class. I'm going to tell you a statement that you can prove by induction, which you should do at home. So the claim is not only is it at the end that you get a spanning tree, but at any end of the iteration of Prim's algorithm, you have this set of vertices S that you have handled, and you have certain set of edges T at that point of time. You can argue that those set of edges T actually connect everything in S. So this is true at the end of each iteration. So at the end, when S is equal to V, you would argue that the final output is a spanning tree. Okay? So at the end of each iteration, S comma T is connected. Okay. So this implies Prim's is correct when S is equal to V. And remember, the terminating condition of Prim's algorithm was you keep on running till S is equal to V. Okay? And again, you can prove this by induction. We are not going to do it now. This is proof is an exercise. Okay. But assuming we prove claim 3, then we are done because we have argued that every edge added is safe, and at the end you have a spanning tree. Evan.
Do you have to argue that S will eventually become T and your algorithm will terminate?
So Evan's question is, do you have to argue that eventually S will become equal to V and our algorithm will terminate? You should. The fact that when the algorithm terminates, S is equal to V just follows from the statement of the algorithm. And the fact that it terminates is whenever you run the algorithm, you're adding a new vertex in. Okay. And of course, we'll also do runtime analysis, so that also implicitly implies that the algorithm terminates. Any other questions? All right, so assuming cut property lemma and assuming all the edge costs are distinct, we have argued the correctness of prims. So now we'll go and prove the cut property lemma, or rather do the proof idea. So let's go through the argument, and we'll have our old friend proof by contradiction back. So the way, again, remember the cut property lemma says, given a graph for any cut, the cheapest crossing edge is present in all MSTs. So the negation of that is there exists a cut for which the cheapest crossing edge is not present in some MST. Okay. So for contradiction, assume there exists an S that's not empty and that's not everything, and there exists an MST T such that the cheapest crossing edge for the cut S and everything else is not in T. Okay. So pictorially, we have our set S, V minus S, and I have this cheapest edge E, which I've drawn with a dotted line to signify that it is not in T. Okay, so this is the situation. And so we want to come up with a contradiction, and the way we're going to come up with a contradiction is construct another MST, another spanning tree that has cost strictly smaller than T, and that would contradict the assumption that T is MST. Okay. So goal is construct a spanning tree T prime such that the cost is strictly smaller, and again this is a contradiction because we assume T is MST. So by definition among all spanning trees, T's cost is the minimum. Okay. All right, so we know that the original graph G is connected. We know it has another spanning tree T prime. It has an MST T. And we know in this cut S and everything else, the cheapest crossing edge E is not in this cut. Okay? But what can you say about the edges in T when you look at this cut? Will T have at least one edge that's crossing or no? Yes, so the fact that since T is connecting all just the edges in T is connecting all the vertices means that if it doesn't pick up any crossing edges, then you've shown two parts that are not connected in T. Okay? So the fact that T connects all the vertices means that it has to pick up some crossing edges, just that it is not T by assumption. Okay? So as T connects all V, there exists a crossing edge, say E prime, which is different from E, that is in T. Okay. Okay. Now, we have looked at exchange arguments, right? So we want to use exchange argument. The easiest thing to do is, well, we don't have E, and we have this other edge E prime. Let's just swap. Right? And the hope is since the cost of E is smaller, we'll win. Okay. So consider T prime, which is what you get by dropping E prime and then adding back E. Okay. So then if you look at cost of T prime, it's cost of T, and I'm dropping E prime and adding back E. Now remember, all the edge costs are distinct, and E has the smallest edge cost. So I claim as CE prime is bigger than E, this is strictly smaller than C of T. And again, the cost of E prime is strictly bigger as E is the cheapest crossing edge plus edge costs are distinct. Okay. So again, the idea is since T has to use some other crossing edge, just throw away that other edge E prime and add this cheapest crossing edge in. Now this new set of edges T prime will have strictly smaller cost because I've thrown away an edge which has a strictly larger cost than the one that I'm putting back here. Okay. And so am I done? All right, true and false question for your group. Am I done or am I not done? And if I'm done, why am I done? If I'm not done, why am I not done? So take a minute. All right, any questions before we go on? Okay, how many of you think the proof is done? Okay, how many of you think the proof is not done? Okay, the correct answer is the proof is not done. Why is it not done? Other than trying to use some sort of reverse psychology that I probably wouldn't have asked the question if it were done. Alejandro?
Never mind.
Okay.
Wait, so, I mean, I guess I'm just gonna ask the question, why is the proof not done? Like, you just showed that T wasn't an MST.
No, I didn't show that T wasn't an MST. What I showed was there exists another set of edges T prime with cost strictly smaller than T. But to come up with contradiction, I have not argued another thing that I need to argue. Stephen.
About T prime itself, saying that it's not an MST.
Or to be more precise, you have to still argue that T prime is a spanning tree, that it's connecting everything.
Oh.
I just said pick a set of edges, throw one guy out, put other guy in, and the total cost is smaller, fine. But I mean, I could have thrown everything out and I would have gotten a smaller cost, right? So I still have to argue that T prime is actually a spanning tree. So that's the thing that I've not argued. And it turns out if you do the argument the way that I have done, you can never guarantee that T prime is a spanning tree. Okay, so let me give you a quick example to show why this is not enough, and then we'll fix it. So it turns out fixing the proof is not too hard. You just have to be a bit careful about how you pick this other crossing edge. Okay. All right. So the answer is no. And so for example, here's something. So let's say my S is so that so let's say this dotted edge E is the cheapest crossing edge. And let's say I have more than one crossing edges in T. Okay? So let's say I have this E prime and E double prime. So it turns out that the endpoint of E prime has no other edges incident on it. Okay, so let's say this is x and y. I mean, this is connected to a bunch of other stuff, but y is not connected. So so the way we did the argument was, while T has some other crossing edge, let's just pick any one of them and it will be fine. Okay? And so in this case, if you pick E prime and throw it away, y gets disconnected. And that's not good. Right? Whereas in this case, what we should have done is picked E double prime instead of E prime. And then we would have been fine. Okay? So the basic argument is, you have to pick the crossing edges a bit more carefully than just saying pick any of the crossing edges. So the issue is dropping E prime would disconnect y. So here's kind of the fixed argument. So I'll denote the endpoints more explicitly. Now let this cheapest crossing edge, one endpoint be u, the other endpoint be v. Sorry, u and w. Okay. And now what we're going to do is not just look at, so again the issue was, we don't want to throw guys away that are, connecting some, is the only lifeline for some other vertex, right? So what we're going to do is note the following. Note that T connects everything, right? Because it has to. It's a claimed MST of the graph, and it doesn't have edge UW, right? So that means it has to connect UW via some other path. It's just that you cannot use the edge UW. So since T is a spanning tree, there exists a UW path without the edge E. Okay, so what that means is you start from here, but the point is, since you're starting from U, which is in S, and ending in W, which is not in S, it necessarily means that you have to have a crossing edge. Okay? So let this be X and Y. So that implies exists a crossing edge E prime on this path. And this is the only difference from the proof that we have done before. Instead of just saying pick any crossing edge, we are saying pick any crossing edge that's on the UW path. And we are going to argue that in this case it is enough. Okay. So now the definition of T prime is again exactly the same as before. So this is E prime. So I drop this edge E prime and add this edge E. Okay. So cost of T prime is less than cost of T as before. It's exactly the same argument, nothing changes there. We just have to argue that T prime still connects everything. Okay. So the claim is T prime is connected. And what do you have to do this? We have to argue that every possible pair of vertices has a path between them, right? So for illustration purposes, let's consider two vertices A and B. One is in S, the other is not in S. So case one, AB path doesn't use E. If that's the case, doesn't use E prime. In that case, we are fine because we only use path, whatever edges we had before, we'll still have that edge, right? So if AB was connected via path that didn't use E prime, that path will remain intact in T prime. So you're good with that. So the only problematic case is, what if the only possible path that connected A and B actually went through E prime? Okay. Case two, AB path uses E prime. Okay, so maybe you kind of meander around till here, go to X, take this edge, and then meander around and go over here. But what I'm saying is, since I'm dropping this guy off, you can just take this longer path now. Okay, so the point is, having E prime and E both together will create a cycle, and I'm just dropping one of the other guys off. So everything that remained connected still remains connected. And this finally proves what we wanted to do. So this proves that the set of edges T prime is connected, and so this implies contradiction. Contradiction to fact that T is an MST. And now we're finally done. So I'll let you talk to your friends for half a minute. Let me know if you have any questions. If not, we'll go on next to see how we use this to prove the correctness of Kruskal's algorithm. So your question is, you don't understand why there has to be UW path with what in it?
Without E.
Because E is not there in T, right? That's the assumption. T is an MST that connects all paths, and the original assumption was E is not.
No, the assumption is that E is.
Because that's wrong. Sorry. Thank you.
Okay.
Sorry. So throughout we have been assuming that the edge E is not in T.
Okay.
Alejandro.
So constant T prime have to be less than or equal to?
No, it's strictly less because we are assuming all the edge costs are distinct. So the edge cost of E prime is going to be strictly bigger than the edge cost. And again, this is a crucial part where you use the edge distinctness property, otherwise you cannot prove this. Any other questions? So everyone okay with the cut property lemma, proof of the cut property lemma, and why the cut property lemma implies that the Prim's algorithm is correct? You guys are really silent, generally not a good sign. Questions? Otherwise I'll just move on, right? So. Is everyone okay? All right, thanks for the sum of the nodding heads, that's good. All right, so what we're going to do next is, now that we have proved the cut property lemma, we're going to argue that Kruskal's algorithm is correct. So we're going to argue Kruskal's algorithm is correct. And as a quick reminder, this is the algorithm that goes in increasing order of cost of the edges and adds them if and only if adding it doesn't introduce a cycle. So consider all edges in increasing order of costs and add it to T if it doesn't introduce a cycle. So again, the goal is, as we did for Prim's algorithm, we somehow want to argue every time a Prim's algorithm adds an edge, it's the cheapest crossing edge for some cut. And again, we want to argue that that's a safe choice. Okay? However, it turns out that unlike prims where the algorithm itself was giving you that cut, there's no explicit notion of cut, right? So what I'm going to do is I'm going to tell you what that cut is going to be. Okay? It's kind of a nice, cute trick. Okay? All right. So consider the time that algorithm is about to add e to t. And when I say about to add, this means when it has already done the check and verified that adding e is not going to create a cycle. Okay, so when I say it's about to add, it's after doing this check. And again, let this be uw. So this question is what is s in this case? And it turns out that the best thing to look at is when I'm about to add this edge e, I have certain set of edges in t. Right? Only using those edges that exist in t, figure out all the vertices that are connected to this one endpoint u. And that's going to be my set S. Okay? So let me write it down. So let S be set of vertices connected to u using only edges in T. Okay, so the situation, the way it looks like, I have this edge E that I want to add. And here I'm only using, again, U is going to be connected to every other vertex in the original graph G because G is connected. What I'm saying is no, only look at the edges T that you have already added so far. Only using those edges that can connect to vertex U, that's going to be my set S. Okay. So the first claim that I make is that S is not, so again, we want to argue, to use the cut property lemma, we argue S is not empty, we're going to argue S is not everything, and we're going to argue that the edge E is the cheapest crossing edge in this cut. Okay? So the claim that S is not empty just follows from the fact that U is connected to itself. Okay? So this is simple. What we want to argue also is that S is not everything, and the way we're going to argue that is to argue that W is not in S. Okay? So claim 2 so we're going to argue that S is not everything, and this will follow from the fact that W is not in S. And the reason is, if W were indeed supposed to be in S, right, that means it is connected by edges in T to U by definition. And now I have not added the edge UV yet. So if I added the edge UV, I would end up with a cycle. Okay? And this is because as otherwise adding E would create a cycle. And the third claim that we're going to make is that E is the cheapest crossing edge for the cut S and everything else. And the reason this follows, and we'll quickly go over it again next time, but basic idea is among all the crossing edges of this cut S, this will be the first edge considered by Kruskal's algorithm. Okay? This will follow E is the first crossing edge considered by Kruskal's. And since Kruskal's is considering everything in increasing order of edge costs, If this edge E is the first crossing edge that's considered by Kruskal's, by definition, it will be the minimum cost. Okay? So all these three claims would imply the theorem by applying the cut property lemma. Okay, so I'm over time, so I'll finish here. We'll quickly finish the proof on Wednesday, and then we're going to move on beyond greedy algorithms to divide and conquer algorithms.